welcome back everybody. Today we're going to jump in. This is the problem that we worked the other day. If you got something other than this number, I think, and I'm fairly confident, that it is going to be a calculator issue. So, as we're going through here, let's just verify that we get the right values looking at this. When we plug in, I'm concerned about everybody trying to do something in one step on your calculator. It's the easiest mistake to make. Do me a favor, when we're doing this, what's the mass of B? It was a person acting on the bicycle. So we got 65 here, and what's gravity? 9.8. And sine of what's the angle that the person makes? That's right. I think I heard it over there, but I couldn't tell if that's really what you said. Okay. We're then going to divide this by what? 0.097. Do me a favor. First, type this in. Like, straight up, type that into your calculator. The only part of this that I'm really worried about is that you're going to forget to change your calculator to what? Degrees. This is a degrees problem. We should be in degrees. You get the fancy one. Okay, so just to show you how it works, let me make sure, yep, so it does a longer step. And we're going to have to start playing around with these towards the end of the year. But there's radians, degrees. Okay, so all the buttons are essentially the same, but you're going to see something really annoying that happens. If I'm looking, so if I want the sine of 20, watch how I'm going to make this. The sine 20 degrees. Okay, oh, it's the sine of 20 degrees. Like that's what it is. If you want the approximation, hit the diamond, enter, it'll give you your number. All the buttons are pretty much in the same spot. Any questions that you have, please ask. All right, what do we get for the numerator? I just gave away my calculator, so I can't check.
I got -400.
How'd you get negative?
Negative 9.8.
Okay, so I'm going to take that number for 450 right now. 450 what?
0.4270.
You got 450.4270. Somebody second that?
Does that seem crazy?
It seems kind of big, and you'll see why I feel that way in a second. And what's the radius of the chain? Ooh, we forgot something. What did we forget here? And I forgot it. If we look at this calculation, FC is equal to the radius. Goodness gracious. We forgot this radius. Take this number, do me one more favor. What's the radius of the bike? The bicyclist pedal. 0.17. So we can just tack it right on the end. It's out of order. That's my bad. This number's going to seem a little bit better. And it did seem big, Huggins, but it was because of me, not because of anything you did wrong. Nope. We'll be okay. And we'll see why this is going to be the case. When you take that number that we had, multiply it by 0.17, what's the numerator become? One more time. When you multiplied that 400 number by 0.17? So just the numerator, because I think you're doing the denominator too. Say it again. 76.57. Can somebody second that? Okay. Now, notice I've only done the numerator up to this point. We now need to divide by r sub c, which is the radius of the chain was what? 0.097. Now, just real quickly, do you guys agree that that's pretty much a tenth? Like 90, like that's almost 0.1. Really close to 0.1. If I divide by a tenth, that's the same as multiplying by 10, right? So in my head, I'm already thinking, if you take that 76.57 number and you divide it by 1/10, we should be about 765. Like, we're close to that. When you actually type it in, because it's 0.097, I want you to have that 76 number divided by 0.097 and then verify for me that we get this 789 number. Cool. Huggins, your mistake was probably because of my mistake with the radius. Okay. Don't know why I left the radius off here. I shouldn't have because I had it written up here as well. Cool. All right. Now, seem doable? Seem okay? Hard? What do you think? We'll find out as we get more example problems with it. Okay, there is another idea here that we're going to address today, and I don't think it's anything that we've ever seen. It has a weird name. What's inertia? That's not the weird part. So, say that again.
Like, I don't know, like not wanting to move.
The resistance or the tendency to resist motion. Like you said, not wanting to move, I'm good with that. Inertia, there's inertial mass. We had the question like that when we were looking in space. Harder to push a chair or a car? Why? It's bigger, it's heavier, it has more inertia, is how we talk about that. Now, lots of the times in this class so far, everything that we've worried about moving has been a block or something that's nice and just regular shaped. We don't have to worry about it. Today, we abandon that nice kind of basic idea and we expand it just a little bit and get into some cooler stuff. So still in 8.2 rotational dynamics, it relates back to torque and angular velocity and all this stuff. We are going to give ourselves a definition for what we call the moment of inertia. Now, right off the bat, the moment of inertia, there's an I in there as well, inertia. Okay, right off the bat, ears wide open. You are going to file this into the very front of your cognitive tasks with physics. This is not time. The word moment does not represent time in this situation. Okay, moment is not time. When we look at this, the moment of inertia, we are going to use a capital I. This is the label that we will use for the moment of inertia. And what this is, if inertia is just the regular resistance to motion, we're talking about a special type of motion in this section, this chapter. What sort of motion are we talking about? Hey, rotational. So if we're looking at this, if I define that inertia is just a resistance to motion, and it's implied that we're talking linear, using our powers of deduction, what do you think the moment of inertia might be? The tendency to resist what? Good. Tendency to resist rotational motion. Can I just say resist rotation? Okay. Now, for this, there are some strange ideas that we see that are awesome with this, but it's really easy to make sense of. We're going to get a whole lot of different formulas. But we only really care about one. The rest of them I will make sure that you have. When we're looking at a mass and we want to spin it, does the shape matter? Now, if you're not sure of that, do me a favor. I don't care if it's your physics book or not. Pick up a textbook near you. Have one at your desk. Yep, there's one right there. Okay. So right off the bat, what is this shape? It's not a rectangle. This is 3 dimensions. It's not a cube either, because not all the sides are the same area. I have rectangles on the top and bottom. The faces are parallel to one another. It's enclosed. There's a better name. Something beyond just a rectangle. Interesting. Starts with a p. Rectangular p. It's a prism. These are prisms. Now, do me a favor, without like playing the guess and check, I'm going to give you a heavier text. Without just playing guess and check, and Fern, there's a whole stack of stuff like up there. Just grab one, hopefully the cabinet doesn't collapse. Okay, as you're looking at it, what I want you to do is I want you to think about it for a minute. I'm going to ask you to spin this somehow. You're going to spin it about an axis. We're not going to actually shove anything through it, but I want you to find the easiest way to spin it and the hardest way to spin it. Keep your finger still, so like if I wanted to, I could hold it right here, and I can try to spin this thing. And I can do it. Control, almost. You got the thick calc book, so that one's going to be harder. Hold it at the ends and try it. Okay, a little harder, right? Okay, if I want to spin this thing, this is like the hardest possible way that I can do it, I think. Pretty sure of it. Give me an easier way to do it rather than holding it at the end. I can hold it at the middle. This is so much easier than it was before. Now, I'm going hot dog style right now, long way. If I hold it this way and I try to do it from the ends, easier or harder than the other way? Why? Harder? Easier? I heard both. Try it. Compare the difference between holding it out like this at the very end and trying to spin it, and then hold it like this and try to spin it. One of them's easier. Love it. Again, some more. Nick says it's way harder to do it long way because there's less leverage. I agree with that statement. Do you guys feel the same thing? Now, if I wanted to go crazy with it, I could even make it easier. This one's hard, but I saw Riley flipping book pizzas over here. This is the easiest way to spin it here. I just can't do it nicely. Now, what we are seeing is exactly this idea of the moment of inertia. Here's the weird part of it. We cannot generalize every single shape with the same formula because every single shape is different. In your notes, I want you to do the following. We're going to add a ring. And it's not going to look like it, but we're going to have a ring. And I'm just going to bold this. Let's say here's a ring. Okay. Now, for this one, we're going to have to assume that there's something I can connect to in the middle. Okay. I'm going to be really specific with the language. This is a ring with mass, and we're just going to say it's mass M, distributed around the circumference. Now, I don't have any big rings other than hula hoops. Circumference. Okay. Now, on this, assuming that we had something to link this to, what do you think we might call this distance? That seems reasonable to me. R for reasonable to call it the radius. Now, this one is the most basic shape, and we're going to deal with this, but I'm going to include one more picture that I don't want you to draw. I just want us to think about. Conceptually, see if we can make it make sense. If I take the exact same mass and the exact same size, but instead of sticking all the mass around the outside like this, if I were to take another ring of the same size, and I'm trying to make it the same size, another thing of the same size, and I went through the painstaking process of equally distributing all of the mass throughout it. So they're the same mass. And I wanted to spin both of them the same way. Which one's harder to spin? Now, for this, to think it out, because it seems like it's kind of a hard question, like completely. As you think about this, here's what I suggest that we can use to think of it. If you take your pencil and we try to spin it, right now all the weight is uniformly distributed, and I know that I can do it like this. Could we stick a weight on our pencil? Do you want to go get clips and stuff to actually stick weights on our pencil? Cool. I'm fine with not doing it. You guys can do it if you want to. I got clips, I got weights. I will hook it up. Now, if I had this pencil and then I moved all the mass to the end, like a baton might be, would it be easier or harder to spin, you think? You think it'd be easier? So we're going to check this out really quick. And so right in the middle. That's a good point though, Nick. I'm going to grab some of these guys. All right. So I'm not going to be able to uniformly distribute all my mass, but I'm going to do something here real quick. I have a single radius that we're looking at. Okay, this is really obnoxious, but I'm cool with it. That was dumb. Why would I do this? Cool. All right, right now, all my mass is near the outside, and I'm going to hold it like this so it doesn't break. If I try to spin it, I'm going to pass this around. I can spin it here. I'm not going to hit anybody probably. Okay, if you want a second to stand up and feel this, I would think everybody should. Don't do that at your desks. I'm going to have you guys stand up and come hold it right close to the middle, and I want you to try to spin it. And just notice how hard it is. While you guys are doing this, I'll go get a different one, and I'll connect the masses elsewhere. Cool. So, do me one favor, Riley or Nick. Will you stand up and using the mouse just on the keyboard, we hit the pause button. It's on the bottom right. And then you guys stand up. I'll go get another one of these. I want everybody to pick it up and spin it. Not violently to hit people with clamps. But pick it up, spin it, feel it. As we look at this, that was not, I wasn't expecting people to say yes, but I'm cool with that. Much easier to move the one with all the mass in the middle, right? Now, as I move the mass closer to the middle, it gets easier throughout the whole process. It gets harder as I move out. So this is the maximum that I'm ever going to encounter for this amount of mass to make it as hard as I possibly can. That mass distributed outside. As we look at this, what we have for our moment of inertia is the following. Turns out that if we have a ring or a hoop, you'll see this sometimes referred to, our moment of inertia is exactly equal to I, this is our moment of inertia, equals m, our mass that we're trying to move, times the square of the radius. Okay, for this idea, this is the very hardest possibility that we can encounter. The ring with all the mass at the outside. Anything inside where we start distributing more of that mass towards the center, or we start changing the shape so that not all the mass is on the outside, it gets easier. When you're looking at this, this is the only formula that I'm going to expect you to be able to recall off the top of your head. I'm not going to write down this whole table for us, but I want you guys to be well aware of this table. When we change these shapes, and I need a document camera, when we change the shapes, we still use mr squared, but we get a coefficient in the front. If I look at this equation that we have, what's the coefficient, the number in front of m right now? It's 1. So if I wanted anything other than this ring, I'm going to have something less than 1. And it is not our focus because we're not in a calculus physics course, but check it out. Here is our hoop, our ring, however you want to think about it. We have an axis, we have a radius, here's mr squared. Anything different, like solid uniform, which I can't make this happen because I'm not a fabricator, but notice if the same mass was distributed all the way throughout it, all the way through, we get 1/2 mr squared. It's half of the moment. Okay, as we get different shapes, there's a whole bunch of these that are different values. The textbook or the rectangular prism that we used says it's 1/12. You guys have access to this. There's a little bit more going on there, but I want you to be very clear. Here it is. Your worksheet has all of them. Cool. Now, as we deal with these moments of inertia, a lot of the challenge is going to be in making sure we use the right formula for it. We have to be able to identify what the object is that we're trying to make move in a circle, or at a circular path at least. So we are going to make 2 quick comments, and then we're going to work a couple problems. So here we go. I'm going to box this one because that's apparently the new thing that I'm doing, making them stand out. And we're going to make 2 kind of warnings about this. First off, we've already written this or said this, but as mass moves closer, and when I say moves closer, we're talking about to the axis that it's going to be rotating around. And what was the shorthand that I used for that? The axis that it's revolving about. Good. The axis of revolution is what we called it, but I'm okay with rotation. As this happens, what happens with inertia? Did it get easier or harder as we move that mass toward the center? Good. The inertia, I, and I'm just going to say I instead. We're going to make this a mathy looking statement. I decreases. Okay, that's our first little piece. Beyond that, like we saw with the textbook, did it matter where you held the textbook? Definitely. So not only is it the size and how the mass is distributed throughout here, but the location of that axis is also a huge importance. Location of AOR matters. Now, if I had a ring like this and I'm trying to revolve here, that's a fairly straightforward problem. If I had my axis here, this problem is much more complicated. How do I want to word this? More than we're going to deal with in here. We're going to get nice axes. Cool. All right. So we have this idea connected in, and I just want to remind us, have we seen radius used anywhere with angular stuff yet? Like if I wanted V, and you don't have to write this again, but this is R times what? Or A is R times something. What is it? Because we already saw these connections. Turn back one page in your notes for me real quick. I think it's one page. I'm going to double check. We made a little table connecting all these linear ideas, and I see it. I see it on yours, I think. No, I thought I did. Got me good. To give you a nudge, this is linear velocity. What's angular velocity? Omega. There's a connection between these, right? Acceleration in the linear sense is the radius r times alpha, or acceleration in the angular sense. Okay, there's one more that we've listed. Delta x equals r times theta. Now, we call this delta x in here. In pre-calc, this is s. That's our arc length, distance we travel. Okay, baller. So let's do a problem or two. We are going to go back to that video, and we are going to start with number... Where did we leave off? We're going to start with number 5. So, surely I have this up. Boom. Look at that. We get moments of inertia, and I can't tell about yours. Yep. So, totally my bad. Your worksheet's better. Never mind. Mine, I had all this on the first page. We don't wind up using all this. Is it on the second page? Is it on the next page in yours? Fantastic. Excellent. Okay, so here we are. We're going to do a moment of inertia problem, and we'll start in with number 5. We have 2 kids, equal masses, sitting on a seesaw. Their masses are way greater than the seesaw. So what I mean by that is we are working with a massless seesaw. It's negligible. We don't even worry about the mass of the seesaw. That makes the problem harder. Okay, as we deal with this, I want to know how much the moment increases when they double their distance. Now, there is a mathy way to do this, and there is a logical way to do this without having to do all the math. First off, if we look at this problem, let's knock it out first. I want you guys to chat. Can you do this without writing anything down? So let me rephrase that. This can be done without writing any of it down and just recognizing the formula that we're going to use, which is this guy, because we have 2 kids sitting on a seesaw. If we imagine that situation, here's a seesaw, here they are, and we have a kid sitting here, there's a kid, and here's a kid. They're beautiful. If this thing were to spin, and I know that it won't because, you know, the ground, but if it were to spin, what shape would the masses follow if we spun it really fast? What would it look like? Kind of like a circle. What about in 3 dimensions? Will it look like a sphere on this? Will they go around everywhere like this? Are you sure, Barsega? You ever seen a merry-go-round that does all the crazy dimensions? Not particularly. But if I take this, and I wish I had this at the end. I need gumdrops or something to stick on the end of a pencil. All right, check it out. Here's a kid on the end of it. If I were to spin this really fast and you ignore the pencil because it's massless, what shape does the compass make on the end? So kind of like a circle, but it's 3-dimensional. Louder? It's a ring. It's this shape is what we would see if we spun it really fast. So when we're trying to make sense of this, when we see a shape and I realize that, hey, this isn't really a ring, but it's going to behave like a ring if we let it spin. All the mass is pushed out to the end. Does that make sense? Okay. So looking at this, I'm going to give you a second without writing anything down, only using what's on the board and this problem. See if we can work this out without having to do any true crazy math and just using logic with what's up here. I'll give us about 60 seconds to try this. Talk it out. You can do it without any writing. We'll do it with writing, of course, but I want to see if we can get it without. Has anybody been able, so I saw some calculating going. I'm not even going to touch my calculator. Has anybody been able to determine the difference? So if not, we will, because check this out. I'm asking you to compare when only one little thing changes. What changes in this question? The radius. Now, in our equation, does the radius show up? Now, what did we do to the radius? It increased by what factor? It's twice as big, right? So if we started with I equals mr squared, I don't know the mass. I do know the radius, but I'm not going to get a number by m times just that. If instead of m times 0.3, we just thought of it as mr squared, and I replace it with m times 2r, because we doubled the radius, right? What happened? What happens when you square 2r? Let's write this down. Original. And this is going to look very different because we don't have a ton of knowns. This is not crazy mathy. Original moment. How would you find it? I equals, what equation would we use? mr squared. Okay. mr squared. We don't know the mass. We do know the radius, but I'm just going to keep it here for now. Okay. If we moved these kids, what changes? If I wanted to find the moment again, they're still the same mass. I'm good with that. And then what? So now this is 2r? And what does this become? 4. And it would be 4r squared, right? I'm going to rearrange it. Are you guys okay with me saying this is what it really becomes? Because it would be m times 4r squared, and I just rearranged it. So if I ask how much is the moment of inertia increase when we double the radius, which is the essential question, how much did it change? So, no, you're good. Do you agree? Thank you for let me know. 2r times 2r. And what does this give me? And this looks terrible. It's right, but I hate it. I just move it out front. Cool. I is how many times bigger? 4 times bigger at this point, right? 4 times larger when radius doubles. Now, there's a connection here. What if the radius were to triple? So careful. If we instead wrote 3r, it's not going to give me a 6 here. It's going to give me 9, right? If I triple the radius, it's now 9 times. If I quadruple it, it's how many times? 16. We're just taking the change in radius as a factor and squaring it. Okay. Easy peasy. Okay. I want you guys to knock out number 6. And let me see if we got to do. Yep. Knock out number 6 for me real quick. Talk it out with your neighbors. There's no real crazy math or nothing. And then we have one more main idea. In physics, we have a few big names. Now, in the last chapter, there were names like Galileo and Brahe and Kepler and Newton. Those were the big names. I want to focus on the last one. Newton. Huge, right? Like, arguably the most important physicist that's ever existed. Like, all of Einstein's work was more complex than Newton's, but Einstein was working on stuff that other people had done. Newton had to develop all of his own techniques. As we look at this, Newton had, I think, gosh, how many laws? So there's a weird way to answer this. More than 3 in the end, because Newton. We saw 3 of Newton's original laws, and then we saw universal gravitation. That's all we've seen of Newton so far. So we're at 4 at this point. But really, if I just ask about Newton's laws, I'm talking about his 3 laws. What's the first law? What does an object at rest do? It stays at rest unless acted upon by some sort of force. Outside, but there's one more important word to it. If I want this to move, and I'm pushing here outside force in here, it's not moving. Why not? Because it's both ways, or it's balanced. We need a what sort of force to make something move? Unbalanced. Okay, that's a first law. Second law we'll hit in a second. That's the law of inertia, if you didn't remember that. What's the third law? Only we had a way to get it if we didn't remember it. I think with 2 words, I could probably stir the memory. For every. What about every action? What sort of reaction? Equal but opposite. Okay, so we have the law of inertia. Stuff that's not moving doesn't want to move. Cool. We have the third law. Normal force exists, and here it is. Right now, we're all feeling it. What was the second one? Force is mass times acceleration. Now, when we're looking at this, we are certainly looking at moving stuff, so it must be accelerating, but it's a different kind of acceleration, right? Because before it was just straight lines. Now we're doing this whole circular idea. So last big piece of this section. We are back to Newton because he's the coolest guy ever. We're going to look at Newton's second law one more time. But instead of looking at it as just F equals ma, we are going to take the context of rotation. So Newton's second law as it applies to stuff that's moving. Now, when we see Newton's second law initially, the way that I normally present it is force equals mass times acceleration. Now, that's fine and dandy. That's a typical way to present it. When Newton actually worded this, he instead said that, hey, acceleration is actually the force exerted divided by the mass. But it's the same thing. It's just rearranged. Okay, this was Newton's idea. Let's take this idea here and try to tweak it just a little bit to be rotational. So, original, living the life here, OG. And then let's do rotation over on this side. Instead of linear acceleration, what do you think we're going to use? Louder and prouder. That wasn't any louder or prouder, but I'll take it. Angular acceleration, alpha. Now, what's the force, if you will, that causes rotational motion? It's not just a force. There's something else that we have to account for. So centripetal is what pushes me in. What if I want to take this and instead of having what causes me to keep moving, what do I have to apply to this to get it to do this? I wish I had something that could spin. I wish I had a fidget spinner. It would be so nice. I'm applying something to make it spin. I am applying a force, but the angle and the lever arm that I'm using certainly play a role. Louder? Torque. Hey, instead of force, we're looking rotational. It's torque. And why is it being the net torque? Now, for this last idea, we briefly touched on a difference between two different types of mass. One of them was inertial mass, that was MA, and the other one was gravitational mass, which is like the weight of gravity that pulls down on something. Now, two definitions of mass that wound up being the same, but they're in different contexts. This one, if I look at torque as the force that I'm using, the mass is what determines how much force I have to use to move something in the linear sense. What is the idea that the resistance to movement that we have in rotation? It's not just the mass that we deal with. It has a specific name. Say it again. What about inertia? The moment. So instead of it being the mass that resists it, it's certainly tied to it, but is our moment of inertia I. Now, we can rearrange this all the same. Torque, if we want, is acceleration times your moment. Like this thing can be rearranged, but I want to make sure that we have this. This is what? Angular acceleration. Okay, just per reminder, this looks really weird. What's the unit on angular acceleration? So you're close. It's radians per second squared, but I like what you said, Fern. Per second squared. Why do I do it like this? Radians are unitless. If you need to write rads here to keep it straight, I'm fine with that, but it's radians per second squared. Okay, what's torque again? This is torque. And I'm not going to write the formula. It's FR sine theta. But if you take an F, what's your unit? Newtons. And what about R sine theta? What unit will that spit out of me? Say it again. Meters. So we get newtons of force times meters. There. That's our unit for torque. And last but not least, this guy. What's I represent? Moment. And can I just write moment? Okay, moment of what, just to be clear? Inertia, love it. And I don't think we wrote this one there a second ago, but what would the unit for moments be? MR squared? What's M? You're right, but what's the unit on it? Kilograms. So there's my M times, what's a radius typically measured in? So kilogram meter squared. Cool. Now, there's some weird stuff that happens because does it look like the units are going to work out correctly here? If you take Newton meters divided by kilogram meters squared, are we left in radians per square second? Doesn't seem that way, but we are, because a Newton is a kilogram meter per second squared. Cool. Cool. I'm not going to make us go crazy into the unit game, but it does shake out in the end. 1 Newton is 1 kilogram meter per second squared, and I know that because I'm taking mass in kilograms times acceleration in meters per second squared. Cool. All right. We have Newton's second law. Last little comment about this. Hypothetically, if we just pretend that torque is greater than 0, and let's just hypothetically say that alpha, my velocity, is also greater than 0, what would happen with the acceleration? So I have a positive acceleration and a positive force. What happens? We did this earlier this year. Will you stand up real quick? Okay, I'm going to be velocity. Here I go. We're thinking linearly. I'm velocity. You're going to be acceleration, okay? Here I am going this way, and velocity, doing my thing. Acceleration is going to push me in the same direction. Now, you got to push me. You got to push me. Too late. Oh, no, that's all right. That works. What did I do? I sped up. Okay, acceleration. Push back. Here we are. Nope. Stand right there. You're going to resist me. Like, turn around. Okay. Push. Your acceleration now. What am I doing? I slowed down. If they're both positive, what happens? We speed up. Cool. What if they're both negative? And I'm going to say alpha increases, and we'll make that other flip statement. If torque is less than 0 or negative, and omega is negative, what happens? And we're going to have to make one little change because it's a weird piece. The force and velocity work in the same way. Then what happens? Speed up or slow down? You got 50% shot. Fern, what do you think? We speed up, but the alpha decreases, right? So here's how we're going to fix that. If I want to say that the acceleration gets greater, but it's more negative, well, how would I do that? If only there was a way to talk about the size of something and not worry about the sign. Oh, my absolute value. Cool. All right. We have 3 minutes to get a problem set up together, and I'm going to give you one problem for your homework tonight. Cool. So I thought I had a second layer. I do. It probably has some pre-calc on it, but that's okay. So I want us to look at one more problem together. We are going to look and start number 7 together. And when I say start it, I'm pretty sure that all we're going to do is get our knowns and our find and our equation, and I'm going to leave it wherever we stop. Okay. We have a solid wheel. Okay, you think that's important, or did I just say that for fun? Why is this part important? The moment is less than mr squared. Cool. So we have a solid wheel. I'm good with that. We have a force that causes torque. We replace a wheel with all the mass on the outside, so that's like a ring, if I've ever seen one. If the same angular velocity were desired, what force would we need? There's a lot going on in this problem. There's a lot going on in like every physics problem. It's really daunting when you read it for the first time. Piece by piece. Let's knock it out. First off, give me anything that we know. What sort of acceleration? So you're right, but the second I see this, is this angular or is this linear? Angular, and what variable do we use? Alpha is equal to 3.25. And I'm going to do per second squared because radians don't really have a unit. If you want to write rads, you can, but remember they can disappear. Okay, beyond that, anything else? I have a force of 4.5 newtons. Yep, capital F. Okay, we have I, and I'm going to call this for ring. And then we are going to take this ring and we're going to change it into a what? Okay, we make it a wheel, right? I'm not going to write wheel though. Check your table for me real quick, and I'm going to keep you like 10 extra seconds. which one of these on this lovely table is a wheel? Because it never says wheel. It's a cylinder. Hoops have all this stuff on the outside. We have eye of a cylinder. Okay, for this, we are out of time. I want you guys to try this. I know that this is mr squared. The cylinder is what, half of it? 1/2 mr squared. I want you guys to attempt to find for me, and what are we doing on this one? We're finding the force required when we try to find our new cylinder, the force applied to the cylinder. Cool. I want you guys to try this tonight. You may or may not get to the end of it. Either way, give it a go. I will be checking for evidence of that in the morning. All right, later Raiders.